Hello and welcome to Mech Zone. In the previous lecture, we have already finished with the chapter on flywheel, and from this lecture onwards, we shall be starting with a new chapter, that is balancing. So, we know that since the machine components or the machine parts are subjected to vibrations, and because of these vibrations, and why are these vibrations created? These vibrations are mainly created because of the variable forces. And because of these vibrations, the machine components are subjected to fatigue. Because of these machine vibrations, the components are subjected to fatigue. So we will be discussing about those vibrations causing forces. These vibrations are causing force unbalanced. Unbalanced forces are produced because of these vibrations, and we shall be discussing majorly about these two types of unbalanced forces. First will be by rotating mass. The other would be by reciprocating mass. So this is called as rotating unbalance, and this is called as reciprocating unbalance. So there are two different unbalances, that is the rotating balance and the reciprocating balance. Now for example, if we have a disc like this, okay, and this is the axis such that it is undergoing an angular velocity omega, and we see that due to the non-uniformity in the material of this disc, the center of mass does not pass through the centroid, and hence it is separated from the exact center from a small distance, and that is called as eccentricity or E. So now, because the center of mass is not lying exactly at the center, it is simply because of the non-uniformity in the material. This can be easily seen जब आप किसी A4 पेपर को लाइट में देखेंगे तो कई जगह पर डार्क पैचेस दिखते हैं, कुछ जगह पर लाइट पैचेस दिखते हैं. जहां पर डार्क पैचेस दिखते हैं मतलब वहां पर मटेरियल ज्यादा है, और जहां लाइट पैचेस हैं वहां पर मटेरियल कम है. तो सिंपली हमें ये समझ में आता है कि जो हमारा जो डिस्ट्रीब्यूशन है मटेरियल का, इट इज नॉन यूनिफॉर्म. तो सेंटर ऑफ मास यहां पर ना होके सेंटर ऑफ मास हमारा यहां हो जाता है, एंड द डिस्टेंस बिटवीन द सेंटर ऑफ मास एंड द रियल एक्सिस इज एक्चुअली कॉल्ड एज eccentricity. This is the disc, and such that this point will be experiencing mr omega square, such that here r is equals to E. Okay, this E is very less, but it is not equals to 0. ये E जो है eccentricity is very less, but it is not equals to 0. Okay, so in the balancing, our main aim is summation of forces should be 0 and summation of moments should also be 0. If these two conditions are satisfied, then we will say that the system is completely balanced. And rotation unbalanced force is always constant in magnitude. If we talk about rotation unbalanced force, so rotation unbalanced force actually has two components. One, it has magnitude, and the other, it has direction. Now since it is rotating, so direction is not remaining constant, but the magnitude of this force corresponding to the rotation unbalanced force is constant. So the process of balancing is actually classified into two major broad categories, and balancing simply means summation of forces should be 0, summation of moments should be 0. Okay, now in case of the balancing, we have actually two types. One is called as the static balancing, and the other is called as the dynamic balancing. Okay, so one is static balancing and the other one is called as the dynamic balancing. So in case of the static balancing, we are able to, or we are mainly trying to balance the forces, but moments are already automatically balanced here. whereas here we are trying to balance the forces as well as the moments, and this is applied when all the masses are rotating in the same planes. When all the masses are rotating in the same plane, then we go for the static balancing, and this is applied when all the masses are not rotating in the same plane, not rotating in same plane. And in case of the static balancing, we will balance only the forces, whereas moments will be automatically balanced, and here we shall be balancing both the force and the moments. Okay, we now come to the topic of static balancing of rotating masses. Static balancing of rotating masses. Static balancing of the rotating masses. So here, when all the masses are rotating in the same plane, because the static balancing can be achieved only when all the masses are rotating in the same plane. Say this is y-axis, this is x-axis. Here we have a mass m1 such that from the horizontal axis the angle is theta 1. We have another mass that is m2, so it is having an angle of theta 2. We have another mass, say m3, and it is at an angle theta 3. Okay, so this distance is r1, this distance is r2, this distance is r3. This is the x-axis, this is the y-axis. The force corresponding to this would be m1 r1 omega square. The sense of speed of rotation for all these masses will be same. We will write m2 r2 omega square, and for this we will write m3 r3 omega square. Okay, so we have drawn the diagram and we have indicated the centrifugal forces that are acting. So all the masses, since they are all rotating with the same speed, hence we have taken omega for all the cases. Now what we have to do is, we will attach an arbitrary mass of mass mb, say radius rb, and such that it is an angle at an angle theta b. So this is actually balancing mass. We are going to achieve the balancing by means of adding a balancing mass. Mass is mb, distance is rb, and angle is theta b. Now after balancing, we already know that we have to balance the forces, whereas the moments have already been balanced. So summation f should be equals to 0. Summation fy and summation fx should be equal to 0, because we have assumed that summation of the forces is 0, and we will take the components of these forces along the x and the y directions. Okay, so if we see that summation of fx is equal to 0 and summation of fy should also be 0, so we will take components of these forces along the x and the y directions. So first, along the x direction, we have summation of fx is equals to 0. We have m1 r1 omega square cos theta 1 plus m2 r2 omega square cos theta 2 plus m3 r3 omega square cos theta 3 plus mb rb omega square cos theta b. Here actually what we have done, we have added an arbitrary mass, say mb, at a distance rb, such that this is at an angle of theta b. Okay, so this was our first equation. What we will do, this is actually equals to 0, so we will eliminate omega square from all these terms. Now we will write summation of fy is equals to 0, and summation of fy equals to 0, we will here opt, or in short this equation can be written as mb rb cos theta b is equals to summation mr cos theta. So this is actually the summary of all these equations. Now summation of fy similarly can be written as mb rb sine theta b is equals to, we will add minus also, it will be minus minus summation mr sine theta. So this was our equation number 1. This was our equation number 2. What we will do is we will square and add equation number 1 and 2. We are squaring and adding. So if we square and add, we will obtain mb rb is equals to under root minus summation mr cos theta whole square plus minus summation mr sin theta whole square, and this will be in under root. So this is how we are going to find out mb into rb, and one of them would be generally given, either the mass is given or the radius is given, so we can easily find out the other unknown quantity. If we divide equation 2 by equation 1, then we will obtain tan theta b is equals to minus summation mr sin theta whole upon minus summation mr cos theta. So there is one note point here which is to be noted, and it is an important point, and the note point is the final signs of the numerator and the denominator will decide the quadrant of the balanced mass. So actually there are 4 quadrants: first, second, third and fourth. So where this mass will be placed, here I have already placed this mass, assuming that it will be lying in the 4th quadrant, but the final sign of the numerator and the denominator will definitely decide in which quadrant it is going to lie. Okay, so for example, if we have summation mr cos theta is equals to plus 4 and summation mr sin theta is equals to minus 3, so tan theta is equals to minus of plus 4 upon minus of minus 3. So tan theta is equals to this would be, I have written the reverse. What should I do? I will write minus 1 here. So this is actually plus 3 upon minus 4, so it ultimately becomes minus 3 by 4. Now tan is negative, so tan is negative in which quadrant? Tan is negative in the 2nd quadrant, and it is also negative in the 4th quadrant. So if we draw the balancing mass, it would come here, MB, such that this angle is theta B. So the final signs of the numerator and the denominator are actually deciding whether in which quadrant we have to place this balancing mass. Here I am not discussing about the graphical approach for balancing, because that is very lengthy and it is not asked in any of the examinations except the GATE. Except ESE. So my first focus is on SSC, JEE and GATE, and I will be completing the syllabus with respect to these 2 examinations. However, later on I shall be adding the videos of balancing with respect to graphical method also. Now we will start with the balancing of the reciprocating masses. Balancing of the reciprocating masses. So before starting this topic, I would like to draw the single slider crank mechanism. Okay, so this is actually fixed. This is point A, this is point O, say this is point B, and the mass of the reciprocating part is actually M. So this is actually undergoing, the crank is undergoing rotation. Okay, the crank is undergoing rotation, and this is the inner dead center and this is the outer dead center, and we know that acceleration is equals to r omega square cos theta plus cos 2 theta upon n. This we have already derived the expression such that this is rotating with an angular velocity omega, and r is the radius of the crank, and m is the mass of reciprocating part. M is the mass of the reciprocating part. Now we know that unbalanced force, that is F unbalanced, is equals to M into A. Now this is to counteract the inertia of the reciprocating masses. This unbalanced force will be generated. So it is mr omega square, keeping the value of A cos theta plus cos 2 theta upon m. So this unbalanced force is always constant in direction, but every time it is changing in magnitude, because the direction is only along the positive x and the negative x. But the magnitude is changing because on changing theta. So this is actually always constant in direction, but every time changing in magnitude. Every time it is changing in magnitude, and this is actually creating the vibration along the line of stroke. This is creating vibration along the line of stroke, and I simply call it as LOS. So we see that this unbalanced force actually has mr omega square cos theta plus mr omega square cos 2 theta upon n. It is actually having two components. This component is called as the F primary, and this is called as the F secondary. Now we know that the value of n was the obliquity ratio L by R, where L was the length of the connecting rod and R was the radius of the crank. The value of n is very, very large, and hence this is very, very small. So primary unbalanced force is very high in magnitude as compared to the secondary unbalanced forces. These both are actually unbalanced forces. One is the primary part and the other one is the secondary part. So now what we will do is we will go for the primary balancing of the reciprocating masses. Next topic we have to start is primary balancing of reciprocating balance. Okay, we'll now start with the primary balancing of the reciprocating masses. Okay, so now we will start with the primary balancing of reciprocating masses. Again, that's a mistake. Okay, so what was done was, we have this single slider crank mechanism, and this cylinder is fixed such that this is undergoing rotation. Okay, so what they did was they assumed that all the mass is concentrated here. Okay, so it was assumed that all the masses are concentrated here. This angle was theta and this component was mr omega square, and mass was assumed to be here. Mass was assumed to be here. Okay, this is rotating with omega, and this is r is the radius of the crank. This is the inner dead center, this is the outer dead center. Okay, so here we had one component, that is mr omega square cos theta, and we had one perpendicular component, that is we had, one second, here actually हमने क्या माना कि इसके जस्ट अपोजिट में एक मास हमने बैलेंसिंग मास लगा दिया B. ओके, सच दैट द लेंथ, ये जो डिस्टेंस था b था, सच दैट कैपिटल B इंटू स्मॉल b ओमेगा स्क्वायर इट वॉज इक्वल्स टू mr ओमेगा स्क्वायर. So omega square gets cancelled out. B into small b is equals to m into r. So here we had the component of bb omega square sine theta. So this thinking that mass was assumed to be concentrated here was actually an artificial thinking. It was an artificial thinking where it was assumed that all the mass is concentrated here. So actually while balancing they were failed in the balancing of reciprocating masses. Reciprocating mass को balance करने में failure मिला. So we will not balance for the reciprocating masses completely. हम completely उसे balance नहीं करेंगे. हम लोग क्या करेंगे, हम लोग सिर्फ और सिर्फ reciprocating masses का कुछ एक portion ही balance करेंगे. So what we did was we will balance them. We will balance them partially. हम उन्हें partially balance करेंगे. Okay, so please stay tuned to this lecture and in the next lecture I shall be starting from this point onwards. तो अगर आपने हमारा चैनल सब्सक्राइब नहीं किया है तो इसे सब्सक्राइब कर लीजिए और बेल आइकन को भी प्रेस कर लीजिए so that you don't have to miss any important updates on important video lectures for various mechanical engineering subjects. So I therefore request you to kindly view this lecture and also share the information to your friends so that they are also benefited at a large scale. क्योंकि हमारे चैनल पे सारा का सारा मटेरियल फ्री ऑफ कॉस्ट अवेलेबल है, उसके लिए कोई भी आपको कॉस्ट पे नहीं करनी है and you can access all the video lectures and all the study material. So thank you so much.